Thanks a lot, and thank you for having me. So I'm going to talk about a movement in a couple of parts, namely shapes, spaces, simplices, and structure, mostly because it sounds fun, but it's really all about geometry, topology, and machine learning, and of course, what that means for representation learning. And we're going to start a little bit with a bummer, namely with the bitter lesson, which you might have heard about. So Rich Sutton said that the biggest lesson from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. Whereas if we seek an improvement that make a difference in the shorter term, we often leverage our human knowledge, but that only thing that actually matters in the long run is the leveraging of computation. That sounds a little bit like a bummer if you ask me. And I also don't fully agree with the statement. I think it has to be read a little bit more in context. So when we talk about representation learning and what we want to do with it, I think we need to remember that there's a little bit of a better lesson here, namely that the machines or the algorithms that we build, they do not have to inherit our cognitive constraints, the cognitive constraints of humans, that is, right? So if we develop novel inductive biases, then this is not in conflict with the search for improved general purpose computational architecture. So there is not a strict dichotomy between those two, and these things are never in conflict. And this is why I believe that looking at geometry and topology is a worthwhile thing, mostly because they contribute different things to the conversation. And this is already where we start with the first thing, like the first movement, shapes. What does it mean to capture the shape of data and why are we interested in it? For me, the main thing that makes geometry and topology fly and interesting is that geometry cares about the fine details and gives us quantitative answers. Things like how far is that object removed from some other object? How close are these 2 points, etc. Topology, on the other hand, gives us fundamental properties and qualitative answers. So things like, is this thing connected? Does this thing have a hole, etc., etc. They are in many ways, in more than one way actually, they are two sides of the same coin. And to paraphrase Gunnar Carlsson, one of the founding fathers, I guess, of topological data analysis, data has shape, shape has meaning, and meaning ultimately begets understanding. So that's the name of the game. That's what it's all about. And I try to give you a list of the different flavors of geometry and topology in practice. But notice that when I say this, there's a nice quote from the book Cloud Atlas, namely, all boundaries are conventions waiting to be transcended. So we have this tendency to put things in a box and then we say, okay, if it's in that box, we don't have to really think about how that box interacts with the rest of the world, right? But really imagine math to be more of a continent uh, with a continuous changes between these different fields. But if you were to ask how things are being related to each other and in which boxes they belong, then I would say there's metric, geometry, topology, point set geometry, point set topology, algebraic geometry and algebraic topology, and differential geometry and differential topology, of course. And these things, they cover different things. In metric geometry, we mostly deal with spaces and distance functions. Pretty straightforward so far. Metric topology is not a thing yet, unfortunately, so you have to develop that for yourself. At least the mainstream math community doesn't really have an umbrella term for that. Point set geometry, on the other hand, is also not something that we typically tend to call by that name. But point set topology, on the other hand, this is all about open sets, continuity, and connectedness. So the things that are like very foundational, very fundamental to your data. Algebraic geometry, on the other hand, is all about algebraic structures, whereas algebraic topology is all about algebraic invariants, so things that you can calculate, mostly with linear algebra. Differential geometry is about smooth manifolds and their geometric structures, and differential topology is mostly about smooth manifolds and the smooth maps connecting them. Or, to make it more clear, metric geometry is about distances, point set topology is about neighborhoods, algebraic geometry is about symmetry and symmetry groups, algebraic topology is about cohomology or homology, differential geometry is about things like curvature and more, of course, and differential topology is about differential forms and more, of course. So if you're a mathematician and you're dealing with any of those fields and I forgot your favorite concept, then please don't hate me too much. This is more of a brief illustrative summary of what concepts might be useful for machine learning research and for representation learning in general. Now, let's talk a little bit about the spaces that are involved in these concepts and in these domains. When we talk about data, or when we talk about topology and geometry, we often have this lodestar in our mind, namely that how can we actually represent the diversity of data found in the wild? And our first concept and our first highlight is typically the idea of a manifold. And when we hear manifold, we think of things like the sphere or the torus or maybe a Klein bottle if you're like really fancy. But in reality, there's more. There's even weird stuff, very weird stuff like this Alexander Horn sphere. So just because it's a manifold doesn't really mean that it's like super nice to deal with in practice, right? And we need something to deal with this type of diversity that we hopefully have in our data sets. And we need ways to structure that and to derive some properties from it. And one way to do that, and this is where Peter Velikovic's famous paper, Everything is Connected, comes in, is the fact that we can use graphs. So to quote from that paper, in many ways, graphs are the main modality of data we receive from nature. This is due to the fact that most of the patterns we see, both in natural and artificial systems, are elegantly representable using the language of graph structures. That's really nice. That's really great. We can use that to our advantage. How might we use that though? Because it turns out that when we look a little bit behind the curtain, there's a lot of different definitions for what a graph is. So some people would say it's a tuple with vertices and edges. You already know that. You could also say, oh, a graph is nothing but a triangulation of a manifold. Or you could say, if you feel very fancy, that a graph is a one-dimensional simplicial complex. Or you could say that a graph is a metric space. Or you could say, oh, well, a graph is just a set system. So none of these definitions is more true or less true than any other. They're all valid in their different contexts. But the point I want to make with that slide is that there's a lot of ways to talk about these things and a lot of ways to translate them. And there's a fancy quote from Goethe, from a German playwright, who said that mathematicians are like a sort of Frenchman. If you talk to them, they translate it into their own language, and then it's immediately something quite different. And I can attest to that because I'm currently learning French for my new job here. So it really is complicated to talk about these things in different ways. And in fact, there's even a lot of ways to construct graphs from data, and not all of these graphs and not all of these concepts are created equally, I would say. So the classical construction that you might know already, that you might have even used yourselves at some point, is that if we start with a data set that lives in a metric space, so we have a distance function that tells us about how close things are, right? We can construct a graph by connecting points to their k nearest neighbors. That's a very simple construction that you see all the time. But this already gives us a very specific type of graph, namely a graph that arises from some prior geometry potentially, right? Namely from this geometry that underlies this metric space. And this is not true of all the graphs that we're dealing with, right? So I would go further and I would say that the attributes in the graphs that we create in that way, they actually reflect this geometry. And so when studying such a graph, we are actually studying its geometry. We are studying the metric space through this proxy of the graph. And through that proxy, something gets lost. We also gain something, of course. We gain something that we can actually deal with, namely this graph. But we should be aware that this conversion is potentially lossy. And the way I like to phrase this, because I really love the Shakespearean way of thinking about things, is right. Some are born geometrical, some achieve geometry, and some have geometry thrust upon them. And so why is that a problem? And this is maybe the most controversial slide in this talk. Maybe I have some others. You can tell me afterwards. I believe that in many cases we're actually not equipped to ask what it means to study a specific graph. And I certainly believe that we need to develop a language or a better language for describing this graph data. Because if we treat all the graphs that we have the same, we are making a mistake. We are ignoring the fact that some have this underlying geometrical information and others don't, right? And I'm not talking about the fact that you can assign attributes to a graph. Of course, you can do that. The question is, semantically speaking, whether that makes sense and what that changes about the model that you throw in there. Because this is about representation learning. And representation learning also means that we ask ourselves what properties the underlying representation has. And so I believe that it's critical and crucial to be aware of the underlying geometry or the lack thereof, of course. So in any case, we need to take a better look at our data to understand that, to understand how to build better representation learning models. Now, this not only applies to graph, this also applies to higher order data as well. We'll arrive at that at some point. But even for graphs, it's definitely already a problem. So much so that we had our first case study in differential geometry with Josh and Jeremy and Michael, where we looked at how curvature helps us actually capture new geometrical and topological properties at the same time of data sets, of graphs in this case. And none of these properties are readily accessible using other descriptors. That was a really nice way to look at data, to look at generative models. And we found that we actually gain a lot of expressive power with respect to this curvature formulation at a fraction of the computational cost. So that was a very nice case study in differential geometry there. But more recently, we found that people were looking into the benchmark data sets themselves. There's a great position paper by Maya Bechler-Speicher and many others on graph learning will lose relevance due to poor benchmarks, where they say this paper calls for a paradigm shift toward more meaningful benchmarks, rigorous evaluation protocols, and stronger collaboration with domain experts to drive impactful and reliable advances in graph learning research, thus unlocking the potential of graph learning. The way to paraphrase this is we saw this as Gondor calls for aid and Rohan will answer. I'm telling you why in a second. I'm a huge Lord of the Rings fan, and finally, due to divine providence, we were able to not only have a case study in metric geometry, but also furnish it with a nice title that is shamelessly borrowed / stolen from Tolkien. It's called No Metric to Rule Them All Toward Principled Evaluations of Graph Learning Datasets. It's joint work with Corinna, Jeremy, and Emily. And in a nutshell, what we're doing there is we're asking ourselves, when we use benchmark datasets to evaluate models, how can we also evaluate the quality of these datasets? So not only do we ask ourselves what it means to learn a specific representation of a graph, we also ask ourselves what this representation actually, means in the end. And metric geometry, a simple set of rules here, a very simple set of tools in this case, it provides a partial answer by telling us, for instance, how disentangled the structural aspects, so the graph aspects, if you will, are with respect to the features. Now, let's go a little bit higher. Let's move on to simplices and see what we can do with those. And if you're an algebraic topologist or any type of topologist really, you might ask yourself, well, why are they using simplicial complexes as a unified data representation? Because, well, simplicial complexes are actually, mathematically speaking, kind of boring and a little bit old school. People now much prefer CW complexes and cellular complexes and stuff like that. But here I'm putting on my virtual computer scientist hat. Simplicial complexes are very awesome for representing stuff at the computer because you're talking about like a very nicely combinatorial representable thing. Most of the things that I'm going to say now, though, they also translate to other types of complexes, to higher order complexes, to CW complexes, etc., etc. But for the sake of this presentation, let's talk about simplices. A simplicial complex is built from simplices, and a simplex consists of a set of elements. So if we have a k-simplex, then we have k plus 1 elements. Thus, a vertex in a graph is actually a zero simplex, if you will. And if we have this nice closure representation and this closure properties, meaning that if we have all the subsets of a simplex in the simplicial complex as well, then we call that an abstract simplicial complex. And the moral justification, if you're searching for this, is that we actually know in mathematics now that we can represent manifolds. Most interesting spaces we can represent somehow by this. Almost like canonically speaking, there always exists a triangulation. This is like a really cool paper from the 1940s and part of my ongoing quest for finding the oldest paper that I can quote and get away with in a talk. So this one is from 1940. Maybe I can find one that is even earlier. It's very well, still very well worth a read. Now, why do we want these simplicial complexes with higher order relationships? Well, in a nutshell, I would say that a simplicial complex enables us to go beyond these standard dyadic relationships that we're looking at typically in a graph. And the best way to represent this is to take something like a co-author network, for instance, which actually has higher order relationships. Specifically, in a co-author network, you can model each paper by a set of authors. And if you look at what happens here, not all the authors have co-authored things together, right? So just the fact that I, let's say, wrote a paper with Alice and Bob, that doesn't mean that Alice and Bob also wrote a paper together. So in a sense, going to this higher order representation, we gain some additional expressivity and some additional insights into how the system is actually set up. This is not necessarily restricted to simplicial complexes. You can have hypergraphs which don't have this closure property. You can have cellular complexes. Of course, you can have CW complexes and many, many more. So if you're interested in this, please check out the work by my colleagues Mustafa Hajish and others, including Theodore and Tolga and Michael, on combinatorial complexes, bridging the gap between cell complexes and hypergraphs. Now, what can we actually do with that representation? Well, there's a very nice case study in point set topology by Chris Bodnar and others entitled Weisfeller and Lehmann Go Topological Message Passing Simplicial Networks, where essentially they take these ideas from point set topology. Remember, in point set topology, you ask yourself, hey, how are things being connected? What are my neighbors? What are like the neighborhoods that I need to look at? And what they do is they say, well, we can now do message passing or in general information propagation over other parts of the higher order complex as well. So instead of just looking at the vertices, we can say, well, there's an edge, and maybe this edge is part of a triangle, and maybe this triangle is part of a tetrahedron, and so on and so forth. And so you can have all kinds of information diffusion, information propagation that makes use of all these entities. And it actually works. It gives you surprisingly good, surprisingly stable results. It's really well worth a read as well. Unfortunately, it also has its downsides. So this higher order message passing, or short HOMP as it's now being called, has some limitations, in particular when it comes to differentiate between different types of data. So there's a paper by Jan Eitan and others on showing that this criteria that HOMP is essentially unable to differentiate between complexes that have several fundamental topological and metric invariants, including the diameter, orientability, planarity, and homology groups. So in a way, this is rightfully called topological blind spots, understanding and extending topological deep learning through the lens of expressivity, because many folks refer to these type of higher order message passing methods as topological methods, even though as these guys prove, they don't capture topological information. That's a little bit of a bummer from the point of representation learning, right? Because you want to have this information, you want to leverage this information that distinguishes two data sets or two spaces. So how can we go about this? How can we make this a little bit better? This is where we tried to come in and pitched a new data set, which is, first of all, marvelous work by lots of talented students, Ruben, Ernst, Daniel, and Mathieu. And the rest of us, we old folks, we supervised, right? But in a nutshell, what we're doing is we're looking at a purely combinatorial data set that consists of triangulations of two manifolds and three manifolds. And these are really, really hard to crack. You can have lots of different tasks there, and there are no node features and no coordinates in that data. So it's a purely combinatorial quest, or if you want to put on a different hat, it's a purely topological quest. And we hope that this kind of data set inspires and encourages different algorithm development, because an algorithm that does well on this type of data has to leverage some kind of fundamental properties. It can't cheat by looking at coordinates or node features or stuff like this. It really has to use the structure. There's some very promising results already out there. In our paper, we found that there's some drawbacks with the current methods, but afterwards people picked that up, including folks like Martin Carrasco, one of my incoming PhD students, who found that there's hope for improving this, which is awesome. Now, let's talk about structure finally. Let's talk about how to bring all of that together and what to make of it. Well, what can we actually do to invent the future? What hopes can we have? Um, I'm with Aristotle there, who says that hope is a waking dream, meaning that you are awake, so you are in control to like achieve this dream eventually, hopefully. And my dream is that I want to be able to fully exploit the structure of a data set. But to do this, we need models that are actually capable of capturing and processing, or leveraging, if you will, information both from geometry and topology. If we do that, then we have a truly nice way of doing representation learning for these complicated data sets. So what follows now in the next couple of slides are some proof of concept studies from my lab that give at least me cause for hope, and maybe they also give you cause for hope. So there's one very nice case study in algebraic topology from a couple of years back, where we developed Toggle, the topological graph layer, which is, well, what it says on the can. It's a new layer to make graph neural networks topology aware. So capable of exploiting certain topological features, in our case, connected components and cycles. We should have pitched this as a topological deep learning method, but this was before that actually came up. There was another really nice work with Max, Edward, Michael, and of course Evan and Carsten as well, wherein we essentially found that many data sets are not topological per se. So if you have the node features in there, you actually don't need the topological information because it's all spoiled. But this set us up for some additional studies later on, where we search for different data sets, where we search for better paradigms to actually show when these type of inductive biases are needed. Now, as a case study in differential topology, I'm also very excited to report this work with Kelly and Celia, which is really one of my most favorite works from the last couple of years, because it's just very funky in that we literally can write everything mathematically very compressed into this one slide. So I can just point to this and I can say, well, we have the de Rham map, and then at the end, we go from singular homology to like simplicial cohomology to like simplicial differential forms, and then we're done. This is of course not really understandable in this way, but I can tell you that in a nutshell, we're learning differential K-forms, so volumetric elements of the data. We learn those using very nice multi-layer perceptrons, and we integrate them over all simplices in the data, so over all graphs and simplicial complexes and so on in the data, and we obtain a shared representation. So the interesting thing is that this method, which we use for graph classification, among other things, this method sees all the individual simplices and learns one aggregated or average representation, meaning that in contrast to a message passing layer, we actually have some kind of basis element that tells us what is going on in the data set. So before I get lost in the details here, I invite you to check out this work, because, for instance, when we have paths in the data that go from one direction to the other direction, we learn a basis element that is susceptible to those type of paths, right? So it detects, oh, there's a path going from left to right, or from top to bottom, etc. And this type of shared representation, this is something that, to my knowledge, we can't get with a lot of other methods at the moment. But right now, I'm also very excited about methods that live directly at this intersection of geometry and topology. And the best one that I know at the moment is the Euler characteristic transform. It's defined by a very simple formula that essentially means that we threshold our data based on looking at it from different directions from a unit sphere, and then we calculate the Euler characteristic, so the alternating sum of the parts of the respective data set. Somewhat surprisingly, I should say that even if you only have a finite number of directions in there, it's a sufficient shape statistic. So that was proven by lots of people nowadays. Mostly the most famous ones are Rob Grice proof with Euler integral calculus, and Justin Curry's proofs with O minimal structures. Very cool reads, and I urge you to look at those, and also to look at the original paper on the persistent homology transform for modeling shapes and surfaces. Now, the interesting thing is that this Euler characteristic transform, or ECT as I like to say, combines geometry and topology by in two very simple ways. The geometric aspects comes from the fact that it's a function from the unit sphere, so you have directions sampled from a sphere, and the topological aspect comes from the actual Euler characteristic that you are evaluating. But more to the point, this can be done in a blazingly fast manner. So together with Ernst, we have this very nice paper on differentiable Euler characteristic transforms for shape classification. And this is such a speaking title to me because everything is basically in there, right? So we show that the ECT can be made differentiable using some very, very nice approximation tricks. We also show that this leads to a fast, expressive method for the classification of point clouds, graphs, and geometric simplicial complexes or other types of complexes. And when I say fast, it really is fast. I was blown away by this. This really runs on Ernst's gaming laptop, and it still outperforms things. We even have some follow-up work there to be continued, but this gives me hope that there is something there where we can leverage good inductive biases and we can actually still win the hardware lottery like a transformer does. Now, in a similar vein, there's work with Julius, where we have local invariance, local variants, I should say, of the ECT, where we get competitive performance in node classification, both in the heterophilous and the homophilous setting. This also just appeared at the recent ICML conference. So where does that leave us? Well, I think it leaves us with a new research field, namely the research field of topological deep learning, even though maybe you want to say geometrical and topological deep learning, but that's a little bit of a mouthful. So maybe let's focus on the topological part first. In this position paper with Theo and many, many others on topological deep learning is the new frontier for relational learning. We focus on the idea of pitching the term TDL to refer to the collection of ideas and methods related to the use of topological concepts in deep learning. And I'm very proud of this dichotomy that we developed there, namely TDL methods can be used in an observational fashion, so can use that to improve our understanding of existing models, for instance, or it can be used in an interventional fashion where we add something to a deep learning architecture to treat data supported on higher order domains, for instance, or to increase its expressivity. And this dichotomy between observational and interventional is actually due to Michael, one of my co-authors, and we had like an earlier survey on topological machine learning, but we resurrected that concept for this type of calculation, for this type of research field here. So I'm very excited about the future here, and I want to leave you with some parting thoughts. So in particular for representation learning, we really have to follow one of my favorite dictums, namely that theory without practice is empty, but practice without theory is blind. So we need both to go hand in hand. We need to make sure that when we build something, that it actually has a use case out there in this whole wild real life, as they say. But we also need to make sure that the stuff that we build is not just cobbled together by some concepts that we had lying around, but that it has an actually strong foundation, because you can only build good things on strong foundations. And I believe that in particular in the field of representation learning, geometry and topology are one of the good ways to give us new inductive biases that we can use to build, among many other things, efficient models. And I also think that if done correctly, we can learn more from less. And what I mean by this is that we can overcome data scarcity, but we can also overcome GPU poorness, if you will. And I think that will be more relevant in the future. Even though we have increases in computational capacity, of course, these increases are not distributed equally. And so if you can learn more from less and learn more with less, then you have an edge over other folks. And I also believe if you're a mathematician on the edge, basically, no pun intended, and you're not sure whether you want to join this type of AI research, I can tell you the best time to join is now, because there's still so much stuff going on. There's still so many things that we don't know, and there's no end to our knowledge, to the things that we can achieve if we look at this from a different perspective. So with that, that's all I have for you today. Thank you very much. I'm particularly indebted to my lab members and many of you who met on these slides, but many more of who are still like lurking in the shadows. And I'm also grateful for the funding received for this work and for many other works, both by the European Union, the European Research Council, the ERC, and of course also by the Swiss State Secretariat for Education, Research, and Innovation. So thank you very much.